Hello, everyone. Let's take a look at the lab while we wait a few minutes. Hi. So log on to your Canvas and take a look at the lab, which we are going to cover the rest of the things that we didn't cover, and also do a little bit more conversions and things. Okay, so we are going to do lab 1 today. Next week, we're going to start working on LC3. So this is the only week that we're going to touch on number system.
Hello.
Hi, how are you doing?
Doing good. I'm on mute for a minute.
Okay. So we'll wait like another minute for everybody to get on. Welcome back to CIS-11.
Okay.
Let's take a look at your lab for today. As we already finished the 6 exercises from the assignment, if you didn't get a chance to work on those, I posted the video on the assignment and the video page, so you can go over the video in case you need to look at some of the exercises again, okay? Make sure that you submit your assignments by Sunday.
By Sunday.
Sunday, yes, that's correct. Any question before we start?
What I did was I downloaded the lab work.
Yes,
to what's this thing called? Something. What is it called? OneNote.
Oh, you're using OneNote?
Yeah.
You know you can use Microsoft Office. Hi, Christian. You can download it. I'll show you how. So when you log on to Canvas, for those of you who don't have Microsoft Office on your system, especially if you're using a Mac, which I suspect that's the case, right? We are going to go to this page right here. Okay. And you will find the link on how to get my Office 365, which is free to you as a student. You just have to log in using your RCCD account. You can also log into Outlook and then use the all apps and select the apps that you want to use, so you can directly use it and save it onto the cloud. With the application installed on your system, you can save it to your computer, and then you can upload it at any time. So you have options to do that, okay?
Okay, I did that. That's where I found the OneNote.
Yes.
But I downloaded it and went to a Windows app, and then I put it into.
You want to use Microsoft Word. So, sorry, I need to turn on my firewall. So that way, you know, you don't have to convert it from OneNote over to Microsoft Word, but you can definitely use OneNote and, you know, to add things to it. But Microsoft Word is also, you know, that's the application that I'm using for this.
So I can just leave it in Word and go from there and write on it and everything. Okay.
Yes, you can just type directly to it.
All right. Are you using iPad?
No, I am using a Windows system. So I'm using a Windows PC. Okay. All right. Cool.
Professor Lynn, I had a quick question for you.
Yes.
I know you talked about the LC3 download. Or were we supposed to do anything for the ARM64 as well? Were we supposed to download any software for that or no?
No, we're not
Okay.
using ARM in this class. The challenge with ARM is that it uses a certain emulator, and there are different versions of ARM. So some professor would teach ARM with a specific simulator, just like how I teach LC3 with this simulator, right? Now, you know, there are different versions of it. So to really consolidate that and get the textbook. So I want to put the ARM information in there for you, is that if you want to learn ARM, it's close to LC3. Instructions, some of them are the same, some are slightly different. The new version of ARM uses C compiler, which if you have Visual Studio, you already have that. So you can just link the packages and be able to build it. That will be something I recommend to practice if you want to pursue that area. So let's go through the course and see how you like assembly programming. And if you want to further pursue that, I can give you some resources on how to expand your skill in ARM and build out, you know, your skills for your job purposes. So that will be something. And also use Raspberry Pi. There are tutorials on ARM using Raspberry Pi as well. And I heard that there is a challenge in getting Raspberry Pi right now because they have a shortage, but you can also stop by Makerspace at Moreno Valley College to be able to borrow a Raspberry Pi or use it there. You know, they have some Raspberry Pi for you to use.
Okay, I just thought I missed something about it, but thank you.
No. Yeah,
All right.
no problem. Always. All right, any other questions before we start? Okay, so let me also check and make sure that we have all of the things that we talked about last time. So we got through the hexadecimal version conversions, and then we also did some arithmetic with hexadecimal. Before we get into 2's complement, I want to touch on octal system. And octal system was used. It was used for some of the legacy computers. So when we say legacy, that's the older systems. As you open up your programmer calculator, you do see octal mode there, so you can enter an octal value. So the difference between octal and hexadecimal is that octal only uses 3 bits. So 3 bits in a byte, whereas hexadecimal uses 4 bits in a byte. And so sometimes you also see systems that use 6-bit bytes and also 8 bits. So that is on the older architecture. And when you look at octal, it normally indicates the base 8, okay? Because if you look at the scale for the decimal that we saw when we did the binary conversion, if you start with the rightmost bit, which is the least significant bit, that will be 1. And then you move to the left, that will be 2. And the third bit, that will be 8. So it's only going to use the 3 right bits. And so here, when you see the number 723 in octal, all that is that we can convert it into our decimal base by doing the multiplication method, just like how we did with a hexadecimal. But instead of multiplying by 16 as hexadecimal, for octal, you would simply multiply it by 8 to the nth power, starting with the right. So here we would take the 3 and we would multiply by 8 to the 0 power. And then also the next digit is 2. 2 is multiplied by 8 to the first. And then the last digit is 7. As it's more significant than the 2, we got to increase the exponent, just like what we've done with hexadecimal, right? So 7 times 8 to the second. Once you multiply everything out, you add them together and you would have your decimal number. So just like before, when we convert to decimal, we would multiply it by the base number to the nth power, starting with the rightmost bit or the least significant bit and go left, okay? And then again, similar to what we've seen in the prior example, this one has 4 digits. So as you go, you start from the right and then you go left. As you go for each of the digits, you're going to increase the exponent when you multiply. After you multiply, you add them together and then you put your answer with the base 10 as the result is in decimal. Okay, so that's how you can convert octal directly into decimal. And as you open up your calculator, you switch to the programmer mode and you do see octal here. So if I punch in 723 in octal, which is a base 8, I would see that my decimal is 467. So that's the answer here, as you can see. So you can definitely use your calculator to verify your answer, but this is how we would manually do that. Okay, any question on octal? Okay. So in CIS-7, I also go over some of the specific as well, just like what they do more exercises in this area. Now, let's say that we are going from binary to octal. How would we be able to do that? As I mentioned at the beginning, we see that 3 of the right bits are going to represent 1 octal digit, right? So let me open up my whiteboard. Let me clear this from last time. So let's say that you have, similar to the example, we're going to do 1, 1, 1, 0, 1, 0, 1, 1, for example. Let's do 2, 3. Let's do one more digit. Okay. So when you see a binary value like this, what you can do is you can chunk them into 3 bits each to represent each of the octal digits. And then what you can do is you can put the scale for the decimal like what we've learned, 1, 2, and 4. Okay, 1, 2, and 4. 1, 2, and 4. Then you add up the bits that have the 1, just like how we did with the binary to decimal conversion. We're going to add up this one, and this one. So that's going to give me 7, right? And then we're going to add up this one and this one. That's going to give me 6. And we're going to add up this one and this one. Oh, I'm sorry. That's 5. I miscalculated that. And then this one and this one, that's going to give me 6. So when we represent this, we simply put an 8 base. So this is the same process as what you would convert to decimal, but in this case, we're only using 3 bits. Now in hexadecimal, we're using 4 bits, right? So you simply just chunk them into 3 bits each, and that those 3 bits will represent one of the digit in octal. Any question?
But in hexadecimal,
So in the hexadecimal case, let's say we do a 1, 1, 1, 0, right? So it will be 4 bits. And so you still do the same thing. You still add up the ones that has the ones, right? You add up this one, and this one. So that will give us, this one is 14, right? And then you convert it to a letter. So A is 10, B is 11, C is 12, right? D is 13, so this is E.
E.
Yeah.
Okay.
And then that's base 16.
Okay, thank you.
Other questions? So here, that's what they're showing here is that we are chunking these up into 3 bits each, right? This one represent this. Hold on one second. Let me draw on my notes. So this one, my computer is not cooperating. This one represents the 7 here. Okay. And then the next one represents the 3. So simply you just put the decimal equivalent scale, right? Like what we've seen in the table from prior, to be able to convert that to octal. So same process, it's just less bits. All right, other questions? Okay, so now we're gonna get to the part for our exercises today. And in this section of the notes, and I'm on page 8, okay, and then I'll take a look at the example on our lab as well. So the way that we would represent negative numbers, or the way the system represent negative number, is that we need to use 1 bit to represent the sign of the value. To humans, when we say positive number, right, like positive 47, right, we would indicate the positive sign in the front. And the system is going to use 1 bit to dedicate that is used for that sign. It's dedicated to that sign. And then the remaining bits will represent the magnitude of that number, how it would be positive or negative. So in C++ or C, sometimes you would see a program that would say unsigned int, right, as the type for a variable. And that simply is a positive integer that that variable is going to store. So when we say unsigned int and then the variable name, let's say var1, and then we would put is with the equal sign and a value, right? So when the computer receives the data, when you initialize that value for that variable, let's say 47, it would convert that value, because it's in decimal, to binary, and it would store it as binary, but it would use 1 bit to represent that it is a positive value. Now that 1 bit can also store the sign if it's negative. So when you say negative, let's say 22, then that will be in C++, we would say sign int is 22, right? For that variable. So it would register the number 22, but at the same time, it needs to represent that as a negative value. How can it distinguish between a positive 22 and a negative 22? It would go through a process, what's called the 2's complement. And in the 2's complement, it would take the binary value of 22, apply the not operator or flip the bits, and then add the 1, and that 1 represents, that 1 is going to store the sign. It's going to represent the sign as a negative. So when we say negative 22, it takes the 22 value in binary, flip the bits or apply the not operator, and add 1. Okay. So that's the process for the 2's complement. And so now I'm going to go to the lab. Okay. And the lab talks about 2's complement. And we would use this to represent negative numbers or negative integers. And you see a lot of this in this class, because at one point you would have to see what the system is storing, right, in that space. And then you have to manually tell it to go apply the instructions to convert it to a value. So when you write a program, let's say you write an assembly program to take 2 times -2, okay? Then you have to make sure that the system sees the -2 when it processes the multiplication, that function to multiply, Okay, so it is very manual in the process where we have to really see at this state, what is the system storing? We're looking at how the system sees these values. So when you initialize a value as a negative value, you have to write the instruction to tell it what to do, because at the processor level, it needs that. It needs to have some kind of instruction to process that value as a positive or a negative, okay, to give you the right output. Now, a lot of this was handled by compiler, right? When you do higher programming language like C++, Java, Python. But at the low level, right, we have to make sure that the instructions is understood by the system to do the right thing. So again, this is just the overall process on how to convert the number to a negative value, or what we call the 2's complement. So let me clear this. Okay, and then let's get back here. So your question is that we are going to take the string and we are, take this binary value and we're going to apply the 2's complement. Okay, and yes, you can convert it into decimal, but we can simply start with the binary. So the best approach in doing 2's complement, right? Let's say you have a decimal number, you need to convert it to binary. That will be the first step. So if I'm given 5 as a decimal value, I need to convert that to binary first. Once you get to the binary value, then you are going to flip the bits or reverse the bit. And simply when we apply this, we just use the not operator, right? Not is an operator that is unary. So it takes the bit and change it to the opposite. So when you have a 0, it's going to give the output as 1. If you have a 1 to start, you're going to output 0. Okay. So in this case, we have 0, 1, 1, 1, 1, 0, 1, 1. Okay, so we already have it in binary format. Then we are going to not this. So the 0 is going to become a 1. The 1 is going to become a 0. The 1 is going to become the 0. 1 is 0. 1 is going to become a 0. 0 is going to become 1. 1 is going to become 0. 1 is going to become 0. So here is the 1's complement. We're not done, right? We have to add that 1 bit to store the sign. So you simply do a +1. So 0 plus 1 is 1, and then everything else is the same. And this is your result. So the 2's complement of this value is this. And this is important because in some of the later lab, you are going to operate subtraction in assembly. And when we subtract something, we simply add the 2's complement. So if I have 5 subtract 2, I simply take 5 plus the 2's complement of 2, which is -2, right? So I would have a 3. The computer only adds. Any question? Okay, so we addressed number 1 of our lab by using the 2's complement. I'm going to help you with the next one. So again, we have a binary value. So 0, 1, 0, 1, 0, 1, 0, 1, 2, 4, 6, 8, 2, 4, 6, 8. Okay. All right, now we are going to go through the ones complement by doing the knot of it. That's going to be equal to, so we're simply flipping the bits. 0 becomes a 1, 1 becomes a 0, 0 becomes a 1, 1 becomes a 0, 0 becomes a 1, 1 becomes a 0, 0 becomes a 1, 1 becomes a 0. Now to get it to the 2's complement, we have to do a plus 1. Then we simply take 0 plus 1 gives us 1, and the rest just drop down because you simply add the 0 in the front here. So that will be 1, 0, 1, 0, 1, 0, 1. And this is your answer. So make sure that we remember these steps, right? Now, if you're given a decimal number, like I said, we would then convert it to binary first, then apply the not operator or flip the bits, and then do a plus 1. Now, in the case where you have the 1 at the end and you have to do the carry, make sure that you apply the addition rule and make sure that the carry is being brought to the left column and then added accordingly. Okay. Any question with question 2 in the lab? Okay, so you are expected to know how to do this for our first quiz and our final exam. There are a few questions that you are going to have to solve. And when we start using the simulator, right, in the upcoming weeks, you are going to see that you need to understand this concept to really apply it with our lab. We will do multiplication lab. It might sound really easy, like, oh yeah, I can write 3 lines in C++ to multiply and loop, right? Or do a running sum in assembly. It takes a little bit more steps to go through, but we have to understand how the processor works because there are developers that worked on adding instructions for the developer to be able to process things like gaming, videos, you know, things like that, how it sees the binary and it utilizes the values for different applications. Any question? Okay, let's move forward. Okay, so we addressed the 2's complement. Let me make sure that I have. Okay, so also the end of the notes. Now, I added in the lab where you would need to do the 2's complement of the hex values. So here it says the 2's complement of hexadecimal value, you need to create the 2's complement of hex integer, reverse all the bits, and then you need to add the 1, just like the binary values, because that 1 bit holds the sign. An easy way to reverse of the hex digit is to subtract the digit from 15, because remember that we need to have 16 in the scale for the hex. And we are going to reserve 1 bit, so we're going to subtract 15. So here's the example, right? You're going to start with the digit 6, And in hexadecimal, as you recall, a 6 in hexadecimal is equal to 6 in decimal. So we would take 6, subtract 15, we would have a 9. So basically you find the difference from 6 to 15. So you would have a 9. And don't worry about the negative, right? In hexadecimal right now, the system doesn't know what negative means, right? Unless it's 2's complement. Okay, so you just look at the difference from 6 to 15, and that will be 9. And then the next digit here is A, and A is equivalent to 10 in decimal. So A in hex is 10 in decimal. And you would take 10, subtract 15, and the difference between 10 and 15 is 5. Then the next digit is going to be C. Okay. And as you recall, C is what? Do you know? A is 10, B is 11, C is 12, right? So 12 or C, okay. So here what they're saying is 3, the next digit is 3. 3 subtract 15 is going to be 12. So that's how we get the C here. So between 3 and 15, there's 12. So 12 is going to be C. And then the last digit is going to be 2. 2. I'm sorry, the last digit is D. D is 13. 13 subtract 15 is going to give you 2. So that's how we get the 2 there. But we're not done, right? We have to add that 1 bit to hold the sign. So we're going to add 1, and 2 plus 1 is going to give you 3. So this is your answer for the example. Okay, so let's do number 3. So number 3 tells us that we have a hex value that is 1, 1, 8, and E. And it's base 16, and we need to find the 2's complement. So at the 1's complement, we have to take each of the digit and find the difference between that digit and 15. So 1 subtract 15, the difference for that is going to be 14, right? So A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So here we would see that this will be E. So, and then the same thing for the next one. So we know that it's E because we already did that. Then for the 8, we're going to take the 8, subtract 15. So I'm going to write it down here. So 8 minus 15 is going to give you 7. So 7. And then lastly, E, subtract 15. And as you see, E is 14. The difference between 14 and 15 is 1. So your answer is that. Any question? But, oh, wait, sorry.
You have to add the
Plus
one.
1. Yes, correct. I just, EE72 is your answer. You gotta do a plus 1. Thank you. So we gotta add the 1. Now, in the case where if it's a letter here, right, you just increase it to the next letter, but if it's F, right, so it would do a carry to the next one, just like how we did the addition with the hexadecimal last time.
Professor, it's base 16 because it's hexadecimal, right?
Yes.
Okay.
Base 16 hex, base 8 octal, base 2 binary, and base 10 decimal. Let's do number 4. Any question with 3 though? And if you want to, at the end, we should have extra time. If you want me to go over something, you can also catch me at the end if you like, or you can come into my office hours. So for 4, we're gonna do 7, 6, 0, B2, and this is base 16. We're gonna find the first, the ones complement. So we simply gonna take 7 minus 15. It's gonna give us 8. Sorry, my chicken scratch, 8. Then 6 minus 15 is gonna give us 9. And then 0 minus 15 is going to be 15, which is F. Right? So B is 11, and that's subtract 15. The difference is 4. So 4. And then lastly, 2 minus 15, which gives you 13. And that is D. Okay. So how do I check this answer, right? You simply plug this into your programmer calculator as a hexadecimal value, apply a negative sign to it, which is the ones complement. So here we're gonna, for not, so we're gonna do the twos complement by adding 1, right? So that will be 8, 9, F, 4, E to the 16 is your answer. Question? Okay, so that takes care of two's complement for hex. Only 2 exercises. Make sure we practice and know how to do this. Okay, now let's come back here. So the next part, we are going to do a little bit more conversion, but in this case, we're also gonna do, we're gonna apply the two's complement as well. Okay. So first we gotta get this to hexadecimal, and then we are going to convert that with to a negative by doing the two's complement. So like what we talked about before, when we're going from decimal to hexadecimal, we are going to use the division method. Okay, when we're going from hexadecimal to decimal, we multiply. When we're going from decimal to hexadecimal, we are going to divide. So I'll do number 5, 6, 1, 1. So when you start with this, it tells you that we are going to start, we're going to treat it with the positive value first. We got to get it to hexadecimal, and then we're going to apply the two's complement to make it a negative number. So you're going to start with an absolute value of it. And then we are going to do a long division. Okay, so 3 times. So this is going to be 18, 21, so 3 remain. Right. What is it 4 times? Hold on 1 second. Let me expand and pull this up so I can use all my toolbar here. 24, 24, 3. Yeah, it should be 3 times. So 18 leaves us with 3 because 21 subtract 18 is 3. Remember 2, so that will be 13 left. And then 13, we're going to bring down the 1. So 131 divided by 16 is going to give you what? 4, 5, 8, 7. Sorry, let me say that.
Should be 8, remainder 3, right?
So 8, 48. So that will be 3. You're correct. So this is important, right? Your R3. But we're not done. We're going to divide it again, right? So let me undo that and then take this over here. 38 divided by 16. So that's going to give you 2 with 2 remainder. So R2. And then we're not done. We've got to go again. So 2 divided by 16 is going to give you R2. So it should be 2, 2, 3. Let me verify this. So if you have a hex, that's 611. Oh, I'm sorry, the decimal is 611. Enter. Oh. Okay. Six. I missed something here. Hold on 1 second. 263.
16. The 38, I believe, is kind of. That 2 should be 30.
Yeah, yeah, that's right. So
Remainder
here,
6.
yeah. So 3 divided by that. Okay. Yeah, I missed it here. So that should be 6. 36 is 2. And then 32, 38. So this should be. Okay,
16 going to 38 two times, I believe. You had it right. You had it. And at the bottom, it should be 32.
Yep. The remainder is.
Remainder is 6, yes.
Mm-hmm. Yeah, because it's 12 here. That's right, 6. Okay. So that will be your 263. So you're going to start recording 263 here. Then once you have this, you are going to find the 2's complement. So 2 subtract 15 is going to give you 13. And 13 is going to be D. Okay. 6 subtract 15 is going to give you 9. And then 3 subtract 15 is going to give you 12. But we got to do a +1. So that will be 13 again, right? So that will be D. To the base 16. Okay. So now when we do this and we do 611, right? See how it fills out all the F's in the front because we have it as quad word. So like the binary, it's gonna fill the 1s in the front. So if you bring this down to, I gotta put it on a word because there are more than 8 bits, right? Because you have more than 2 digits. So you would have 611 negative then you would have FD9D. So we should indicate the F here to indicate that it is a negative. But the answer that we derived mathematically is this. Okay. So when you see all the F's in the front, you should know that it is negative. Question? And then we would do the same thing for number 6. So you would take 2885 and then do the long division. Once you get your hexadecimal, then you would do the 2's complement by subtracting 15 for each of the digit, and then add the 1, and you would have your answer. So I'll let you do that one. Any question regarding conversion and finding the 2's complement? Now we're also going to go the opposite way, right? So this one, we are going to go in reverse, where we were converting from decimal to hex, where we divide. So now we're going to multiply. So this is just going to review the last time we talked about this in the last session, right? So what the step 1, it tells you that you would, if you have a negative value, you create its 2's complement or otherwise retain the integer using the integer from the last step. Then if the original value is negative, attach the minus sign when you output the decimal value. So we would start with 5A 2A, and we're going to treat it as how we would be an absolute value, so we can find its 2's complement, okay? And then we simply attach the negative sign when we output it, okay? So again, we are going to do the 2's complement of this. So 5 subtract 15, we are going to have 10, which is A, okay? And then 2 subtract 15, that's going to give you 13. And that is going to be D. And then A, subtract 15, which gives you 5, because A is 10, right? So 5. Now it tells you here that we need to make sure that we get the 2's complement and retain the integers and then convert it to decimal. So in the 2's complement, so we simply only have the 1's complement. So the 2's complement, that's going to make it 86, right? We got to do a +1 here. So that makes us, we have the 2's complement now. Any question with this step right now? Then after this, what we're going to do is we are going to take this and we're going to do the multiplication because it is base 16. So we're going to multiply it by the 16 to the power of n for each of the digit. And we are going to add it. So I'm going to erase this part and so I can continue. So now when we do this, so we have AD6 to the 16, and we want to make it into a decimal. So we're going to start with the last digit on the right. Okay, so we would have 6 times 16 to the 0 power. And we're going to add it with the next digit, which is D. And D, we learned that D is 13. So we would take 13 times 16 to the first. And then we are going to add it with A, which is going to be 10 times 16 to the second. And so this is 1 plus, right? 13 times 16 and so on. So you can take your calculator. $208 plus 16 squared times 10. 2560, and then you operate the addition, you would have your answer.
Wouldn't 6 times 16 to the 0 be 6, not 1?
Oh, I'm sorry. Yeah, thank you. So we would have plus 208 plus 62774, and that's base 10. Yeah, this is 1. This is 6. You're right. So this one, in that step, we simply take the value, convert it to make it 2's complement, right? And then we would do the multiplication after we got the 2's complement, because we need to find the opposite of this number, or the 2's complement of that number. Yeah, that is correct. So you apply the sign when you write out the answer, 2774 negative. That's the step 2 as indicated here. And that's why this part was added to carry this. Okay, let's try the next one. So this is the only week that we're going to touch on this, but we need to know how to do this as we program. Okay, so I'm going to do 604E, 604E, and this is in hex. And so we need to find the 2's complement of this first. Okay. So 6 minus 15, we're going to get a 9. 0 minus 15, we're going to get a 15, which is F. 4, the difference between 4 and 15 is 11, that's B. And E is 14, the difference between that with 15 is 1, but we have to add the 1, so that will be 2, base 16. So after we found the 2's complement, and we multiply that out. So 2 times 16 to the 0 plus B, which is 11 times 16 to the 1st, plus F, which is 15 times 16 to the 2nd. Let me rewrite that. Then lastly, our 9. So 9 times 16 to the 3rd. And then when you have your answer, you would carry the negative and then add this up. So we would have 2 plus 11 times 16, 176 plus 16 squared times 15 . 3840 plus, and lastly, the last digit, so 16 to the 3rd times 9. 36864, and then we add it together and apply the negative. So this is expanded from CIS-7, right? For those of you who learned CIS-7 in my class. So you simply can do this. Now, another way to approach this is to take the hex value, convert it to binary, and then do and convert from binary to decimal. You can do it that way. But you still have to operate the 2's complement when you get to the binary, remember, because it is an assigned value. So when you convert, you would treat it as an absolute value, convert it to binary, get its 2's complement, and then make it into decimal. So that is maybe an extra step or two compared to doing it this way. Okay, so you can do it that way as well. Question? Okay, so I want to spend some time talking about operators. We are going to use and, not, and you know, when we apply conditions like if and else statement in your program, sometime we would, just like how you write it in C++, sometime we would need to be able to apply the operator. Also, you would find that some of the operator will output, you know, specific value that will be equivalent to using multiple operators combined. So here, earlier we talked about having the not operator, right? It's a unary operator, and sometimes you would see the little, it looks like a minus sign with the drop down angle, right? Or they would use like the tilde, which is the wiggly sign. Sometimes you see it written that way. So when we see not X, right? Basically, it's gonna be outputting, when it stores that value, it's simply flip the bits for that value, okay? Now, flipping the bits doesn't have the bit for the sign, so when it becomes the negative value, then we have to add the 1 because it has to be 2's complement. So when you operate the not operator, it's simply flip or reverse the bits. And then when you're writing the and like this, okay, you can also use the hat, but you can say X and Y. We often see the and operator. So in C++, when we include the and in our statement, right, the conditions on the left and the right of the operator has to be met in an if statement for it to be true to execute the body. And the programming concept is the same for all languages. So if we understand how that is in C or C++ or Java, right, we would then apply the same concept here in assembly, because programming concept doesn't change. It just, each language would have different syntax, format, and so on. For the or, sometimes you would see it written like this, like a small v, X or Y. Okay, and the way that we read the not or nor, right? So it's simply going to operate the not first and then apply the or. Okay, so the output of the reverse bit and then use that for the or. So the and the or, it needs two input, X, Y, X, Y, okay? Where not only needs one input. And then nan or not and, sometimes it's written with the and not. So you would then use the not operator with the and, okay? So based on the truth table, okay, we can simply do the not expression here, just like what we've done before. So when you take this and you apply the not to it, you simply reverse the bits or flip the bits. So the one here is going to become the 0. The 0 here is going to become the 1, and so on. Okay, so we have 0, oops, 0 here, 1, 0, 0, 1, 0. So it only requires one input. And so when we subtract an assembly, right, we have to tell it that we are going to not the value at this register, which is where it stores your integer or your initialized value. Then we're going to add the 1. We have to do a +1 to make sure that it is a 2's complement before we can do the add of that negative number to subtract it. Okay, and then again, for the next one is easy. So we are going to do a not. And I'm not specific to how you want to write this. You want to use the symbol, you can. You know, but the important part to take away from this is to understand how to use the operator. So the 1 becomes the 0. And then the 0 becomes the 1, and the 1 becomes the 0. Do I have an extra one here? 2, 4, 5, 2, 4. Yep, I think I have extra 0 typed in there. Yes. So when we operate the not operator in the 2's complement process, we call this the 1 complement, right? So when it gets to this stage, That's the ones complement. When it nodded, it flipped the bits. But it's not completely a negative integer until you add that one bit to hold the negative sign. And that's important to remember because, you know, in CIS-7, sometimes when I go over this, right, and the students, they just go through and do the process, but are not understanding why that one was added. So when you add that one bit, it's simply used to hold the negative sign. Okay. So here we have the AND operator, and notice that when it is false and false, it's false, or 0 and 0, it's 0. 0 and 1 are false and true is false. So anytime you have a 0 as an input out of the two input in the using the AND operator, you're going to have a 0 as the output. Anytime the condition is false, it's going to output false with the AND operator. And then true and true are 1 and 1 is 1. So on the bitwise level, the system see the Boolean, right? True, false as 0 and 1. And I also put it into the table there. And I took the screenshot from another textbook. So we can just type out the answer. You don't have to line it up exactly. I just put it like this so it's easy for you to see. Okay. And so we can go from, let me try to do this so you can see it. Okay. So 1 and 0 is going to give you 0. 0 and 0 is going to give you 0. 1 and 0 is going to give you 0, because remember what I said, when there's a false or a 0 in the mix for one of the input, we're going to have a 0 or the false as the output. 1 and 1 is going to be 1. And keep in mind that this is not addition. Okay, so 1 and 1 is going to give you 1 because the rule here, right? And then 0 and 1 is going to give you 0. 1 and 0 is going to give you 0. 1 and 0 is going to give you 0. So when you have this value, right, as binary, and you operate the AND with another value, this is the output. Question. So we can, so I'll highlight this. We can do the next one. Oops. Let me check it out, underscore here. Okay. 1 and 0. Anytime we have a 0 in the mix, it's a 0. So we would do 0, 0, 0. 1 and 1 is 1. 1 and 0 is 0. 1 and 1 is 1. 0 and 1 is 0. And 0 and 0 is 0. So also on quiz and test, you're expected to know how to use not and or, NAND and NOR operator. So if we need to do a NAND like this, we would simply take the and NOT it afterwards. So it goes an extra step. Any question with and? Now, if you do read the chapters, the first 2 chapters, it does talk about number representation and, you know, what the system sees. And then the later chapters, it's going to go into LC3 and then correlate LC3 with C. And in our case, we'll talk about C++. So the difference between C and C++, do you know the difference between C and C++? That C++ is object-oriented where C is not, right? A lot of similarities, but C++ is object-oriented where you can build class object, right? And you would use that object to access the attributes, or in the case, your attributes would be your variables and your functions, where C, you cannot build objects, but you can write functions the same way you would have to use type, or you can use void. Okay, let's talk about OR. So here's the truth table for OR. And in the case of OR, anytime one of the input is 1. So C# is mostly used for Windows applications, and syntax definitely is different, okay? You would also use C compiler to build C# applications. Often that you will find C# being utilized for, you know, writing applications like you would see in Windows environment. This is why if you're using Unity, Unity is made to be used to develop like things for Windows system. So you would need to program it in C#. Okay. And still object-oriented, all the C-based, you know, you're gonna see a lot of similarities in how we utilize certain write statements and things, but syntax is different. Okay. All right, so for our OR, anytime that you have a true or a 1 in the input, you're gonna have a 1 as an output. You're welcome. Yeah, down the line, I will be working on a C# certificate for the college. It's just a lot of things happening right now, so I'm gonna make sure I make some time for that. Okay, so let's look at this truth table, and we're gonna solve the next 2 questions. I have it underscore, so let me take that out of the underscore here. Okay, so 0 or 1 for question E is gonna be 1, because anytime that you have 1 as an input, right, out of the 2, you're gonna get a 1 as the output. 0 or 1 is 1. 1 or 1 is 1. 1 or 1 is 1. 1 or 1 is 1. And same with the next one. 0 or 0 is 0. 1 or 1 is 1. And you notice that the output for this is the same as one of the input. And when it ORs it with this. Okay, so you can do F. I'll help you start with that. Okay, so 1 or 1, we would have 1. 0 or 1 is 1, and so on. So just look at the table and then look at the rules on the table for the truth table, and then apply that to find your result. Anytime that you have 1 as an input in for OR operator, you're gonna have a 1 as an output. In the AND operator, anytime you have a 0, you're gonna have a 0. Any questions with these operators? So you will find similar questions to this on quiz and test. Okay. Now, if I'm going to give you an example. So let's say, and you don't have to add this to the assignment. Let's say that we're doing a not or a nor, right? For this one. So after you have the or, you're going to take the result and you're going to apply the not to it. Can't seem to be very coordinated today. So when we nor the values, then it will just go to the next step where it would be not the or, okay? Now, next week, I know that I also go over this in 7 when we talk about gates and how gates are being used. And in the book, it touches on that. So we'll take a look at how the gates for the operators and with the input. And then we'll talk about multiplexer or mux, where we would have a combination of, we would have 2 input, and then we would have a combination of different operators being applied to give us a certain type of output. Any question? Okay. So I have a little bit of time, and that was all that we need to do for the lab today. I see a chat question. We know that like the double ampersand or the double pipe stand for and or in C++. Do those operate? Yes. So it is equivalent to those, right? So in C++, you would use those symbols to indicate the and, the or, right? And then you use the exclamation point for not. So when you say, while, variable 1 is not this, right? You would use the exclamation point with the equal sign. So in the case where this is just a way to show or display the operator, right? At the bitwise level, it operates the same, whether you're using an ampersand in C++ or the double ampersand, and then, or the double pipe for the or. Just C++ uses those symbols to indicate and or, right? But in assembly, you simply type it out because low level, right, it understands the instruction and means this, right? Not means, right, reverse the bits and so on, because the processor, that's how it was instructed to do. So analogy for this is like how you teach a child like a specific thing, and that's what when you want that child to complete a certain task, you just use that instruction that you taught the child. So can you go converting the decimal hexadecimal again, please? Yeah. You wanted to do the negative one that we did in the lab today, Brandon? Or do you want to just do a conversion from the last time? Okay, so let's do just regular hexadecimal first so we have a clear understanding. Okay, so, oh yes, negative. Okay, so let's do one with the negative. All right, so if we have a decimal number, let's say 504 base 10, and it is a negative, and we want to make this into a hex number, base 16, right? So when you're going from decimal to hexadecimal, you are going to divide. So you are going to take this 504, right? You are going to convert it to hexadecimal, and then you're going to do a 2's complement to make it a negative. Okay, so first we're going to do a long division. Okay. So 504 divided by 16, we're going to take 50 divided by 16. That will be 3 times. So I should have 2 because that's 48. And then I bring the 4 down, right? So that would be 1 time. So 24 divided by 16. And in this case, what we would have is when we subtract 24 with 16, we should have 8 left, right? So the remainder here is important. So I would make a note of that. Then I still have a quotient here and I would go again. So I would take 31 divided by 16 again. And that will be 1 time with the 15 remainder. Now I'm not done because there's still a quotient here. So I go again, 1 divided by 16. That's going to give me 1 as a remainder, right? Because it's 0 time with 1 remainder. So now at this stage, if you want to check your answer, right, you would go here. So if we simply make, if it's an absolute value, 504, okay, and 15 here represent F, right? So as you can see, it's the last step is the first digit. So 1, F, right, 8. But we're not done. This is only going to give us the positive value of 504. Now we have to take this hex value and we got to make it a 2's complement to represent the negative number. Okay. So after we divide and found our hex value, that would be the positive of 504, which is 1F8. Then we would take that value, 1F8, I'm going to write it here, and we need to apply 2's complement. And the way we do 2's complement is that we're going to take each of the digit and we subtract it by 15. So 1 minus 15, the difference is 14. And in hexadecimal, 14 is equal to E. So that's the first digit. F is 15 minus 15 is going to give you a 0. And 0 is 0 in hex. That's the next one here. And then lastly, 8 minus 15, and the difference is 7. But we have to add a 1 to make it a sign, right? So the 2's complement of 1F8 is actually E08. Okay. So negative 504 is that.
So, Professor, what does that look like on the calculator?
FE08, A08, I should say. You just put the F in the front. So that F just indicate that it's in the negative hex value or a sign, I should say. We should stay away from saying negative because the computer only says sign, right, when it adds that sign for 2's complement. So yeah, FE08. And I have my mode as word, so this will store the 16 bits. So that would carry, you know, and in the in a larger decimal number, when you convert it, you got to change the size of the storage. So that way it would be able to store all the hex value. Otherwise, it's going to cut it off.
Okay, thank you. I was having a hard time, and I had it on keyword, so I got it
Yeah.
now. All right.
Yeah, so when you make it on keywords, right? Yeah, because when you put it on by, it cuts it off. So if I have it on keyword, let's say I have 504 and I apply the negative to this. See how it just fills out the rest of the word, the quad word with Fs. It would just fill out the rest of that, and that would know, you would know that that's represent a negative number to us human, right? Our decimal system. And then if you make it 32-bit, it would just also put the S in the front, but just the storage is less there. The size is smaller, I should say. So knowing this is, you know, now I see some student that they would take this and then make it into binary, and we just learned at the beginning how to do the 2's complement in binary, and then from the binary, and I'll show you that right now since we have time. We have quite a bit of time. So are we okay with this? Can I clear it? Okay. So I'm going to show you another technique that's using binary. So let's say we're going to do, let's do 8, 2, 1, right? And this is our decimal number, and we want it to negative. Okay. And then we wanted to do it, we wanted to go through the binary method. So, but we still want to output the hex, however, okay? So we wanted to see base 16. So then what we can do is we can use the subtraction method, or we can do the division method. That's really up to you. Okay, so I like subtraction because it's just easy to go through. So 1, 2, 4, 8, 16, 32, 64, 120. Let me redo the scale real quick. Closer to the right. So 256, 512. And I can stop there because after 512, which is 1028, it's too large to subtract anyway. So the first step is to, when I convert this to binary and then from binary to hex, I would need to put down the scale if I'm doing subtraction method. If I do the division method, right, I simply take 821 divided by 2. If there's a remainder, that bit is on. If it's not remainder, that bit is off. So whichever method is easier for you. Okay, so I would have 821 and I would subtract 512. Okay, so this and this is going to be 9 and 0 and 3. So I put that bit on. And then 309, I can subtract the next number on that decimal equivalent scale. So 309 minus 256. And that says 3, 5, and 53 left. Put the 1 on top as you subtract it. We're going to skip 128 because it's too large. And then we are going to skip 64. It's too large. We can't subtract those. And then 53, you're going to go again and you subtract the next number, which is 32. So that's 1 and 21. And then we can subtract the next number. So 21 minus 16. That's going to give me 5. We're going to skip 8. And you already know it's 4 and 1 last, right? So 5 minus 4. That's on. Skip 2 because after you subtract, you have 1 left. And then 1 minus 1 is 0. You subtract until you can't anymore. So this is your binary. Then the next step is you are going to chunk it, and you will need to start from the right to 4 bits because 4 bits represent hex. And then if there's less than 4, you fill in the 0 in the front. And we are going to use the same scale, but in the hex, it's only going to go to 8 here. So 1, 2, 4, 8, right? So this is really easy. So I'm going to erase this because now it's going to confuse you right there. Okay, so I'm going to replace it with only 4 numbers now. Okay, so we use the scale to find our binary by doing subtraction, or you can do the division method. And then after that, the next step is to chunk it into 4 bits each, and each of the 4 bits represent 1 hex value. Actually, I apologize. When you get here, we would do a 2's complement. So now we're going to do the 2's complement before we convert. Because if we convert now, we have to do the 2's complement in hex, which is also another step, right? So either way, so since we have it in binary, we are going to do the 2's complement now before we chunk it. So flip the bits. We're going to knot it. So 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0. Okay, so after you knot it, you got to add the 1 to make it a 2's complement, because remember, it is a sign value, right? So we are now going to add the 1. So either way, if you do the 2's complement here, or when you do the 2's complement in hex, it's still going to be the same answer, right? So here we simply add the 1, which gives us, I'm trying to make room on this whiteboard thing because it's, it would just be that value with the 1 added. Okay, so that will be 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, right? Because this is just going to add and put it here. So now we have the 2's complement of the binary that one after we convert. Okay, then you are going to chunk it and to make it hex. See, you notice that when you do this, you have some extra steps. Okay. So now when you get here, basically you are going to put in the value, right? 1, 2, 4, 8. So this and this and this adds up to be 11, right? Which is B. Then again, 1, 2, 4, 8. Those 2 add up to be 12. Which is C. And then 1, 2, 4, 8 again. That's also 12, which is C. So it's C, B, C, B. So in this process, we go from decimal value, convert its absolute value to a binary. Then we do a 2's complement in the binary. Make sure that we have the 1's after the 2's complement, right? And then we chunk it into 4 bits, convert each of the 4 bits into hexadecimal value, and you have your answer. So that's another way. But as you can see, this is also extra steps, right? So if you're comfortable with this, that's fine. Other questions? I want to touch a little bit on concept, as I didn't get to do that last time on processor, and talk to you a little bit about processor and assembly language and gates. So that kind of helped give us a little bit of understanding going into the next session on Tuesday. So as I mentioned last time, when you work with assembly, you will find that assembly is often referred to as ASM programming language. There are many different types of assembly language. ARM64 is one of them, right? And sometimes you would see MASM that is used by Microsoft. So like x64, there are quite a few Intel processor that was programmed using Microsoft assembly language, MASM. So some professors, they would teach Microsoft ASM. I started out doing that at MBC, but I found that it was very challenging for students to learn how to do it because the instructions, and there are a lot of instructions and steps that's involved, but you can still write a program with, GUI and all, right? There are libraries that you can incorporate even at the low level. Or sometimes you would see NASM, and assembly language can be used to create compiler, can be used to make browser, even simple applications, but ultimately it is programming the processor. So we use ASM to program human readable program correspond to exactly what the machine language would be. Now here it talks a little bit about, and you find this document in your notes. And the disadvantage of this is that you can't, everything needs to be explicitly described and it has to be very precise. And so number system, the computer is a calculator, right? It was designed to do arithmetic calculations in the 40s. And so the model of this is, we still utilize a model that was derived by von Neumann. And so it's still, we have the same system. It's been advanced to understand more advanced instructions. Now, when you write it in higher level languages like C++, C#, Java, Python, right? It is never going to match the raw speed and the efficiency compared to the assembly, and that's the advantage. So even though there are many lines in assembly, the computer processes assembly language much quicker because when you write it in higher languages like Java, things have to be compiled. Okay, so the compiler has to build your program. Whereas at assembly level, it is closer to the low machine language where it is, the raw speed is faster. There's efficiency. Now, the mid-level languages or the low-level languages, there's some abstraction, which is a little bit easier. This is used to write OSs. Okay, now you often see that the components of OSs can be applied to the higher language, and most developers today use the higher programming language to build the components in the OS. But when you're looking at drivers and hardware abstraction layers and things that where your operating system needs to talk to your hard drive and inputs, right? We incorporate libraries and things for that, but when you're working with hardware, a lot of the times you would need to do low level or mid level. Okay, so I want to really clarify this because when you finish this class, people are going to ask you, right? Let's say that you said you learn assembly and they're going to ask you, which architecture have you learned? And we are learning RISC architecture. Okay. and we will expand a little bit more. So when you look at ARM, right, it is in the family of RISC. So you would likely see similar or almost the same instructions being used. So when you're looking at like Raspberry Pi processor or some Android, right, base processor, right, Snapdragon and things like that, they use ARM. Okay, and RISC stands for Reduced Instruction Set Computing. Make sure we know this. There are billions of ARM chips that were produced years ago and much more now. Okay. So ARM uses the instruction set architecture, which is ISA. This is mostly produced in the industry. It can be fast produced. If you ever use an Arduino, which I love, right? It uses AVR assembly. When the user interface with the Arduino to program, you use C language, but at the hardware level, they use AVR assembly. You do see some simulator being released for this, okay? And then another ASM is your net wide assembler. This is used a lot on Linux systems. So when we teach NASM, you often build that with Linux. This can be also used with Intel x86 architecture, which is very common. That will be for your 16-bit and older, like I want to say Windows 98, right? This is Windows XP era. And then now we would see the x64-bit, x86 to x64. This is the most commonly found for use for assembler for Linux systems. Okay, and then I talk a lot about Microsoft ASM earlier. So those are some of the assembly language that you would hear or see. Okay, any questions? Okay, so I'm gonna go a little bit more and then I'll let you off for the night. So I wanted to let me double check something. Okay, so I'm gonna touch, so as you can see, I built so next week we're gonna do Hello World in assembly, okay? And it's gonna build all of these files so you're gonna see, okay? All right. So let's talk a little bit about gates. And some of you have seen this from my notes from 7, so it's the same. In the processor, your CPUs that you buy, whether it's an i9 or an AMD, or when you're looking at your smartphones, when you purchase your smartphones, an Apple phone or an Android phone, your processor, your microprocessor are just simply constructed with digital circuits. And we talked about how 0 represents 0 volts, and then the 1, right, when it turns that on, that represents the 5 volts. So the digital circuits are constructed from what's called the logic gates. So at the simplest level, your processor are just a group of logic gates that is built into digital circuits. Now, I show this to all my students when I talk about processors. So what does that really look like? Okay. And what they use is at the smallest level, and sometimes you see them larger than this. So if you use Arduino, sometimes you would use a transistor like this. Okay. So the building blocks of your computer hardware is your transistor. Okay. This is going to give you source, sink, and gate. And the book talks about that. So when you buy an Xbox or Nintendo Switch or so on, right, the processors are consist of millions of transistors. And we're able to build a microprocessor, a very tiny microprocessor with billions of transistors inside. So these are the working units of your microprocessor. Okay. So that link gives you this page where it shows you, and the book talks about how the gates and the source would be. Okay. So when it's off, you can visualize it. It would be like this, like your faucet at home, where the gates would close and you would not have the source. It would be off. And then when it's on, it's going to open and there's a flow. Okay. So to build the bigger circuits, and I hinted on this earlier. So for example, when we're looking at like a NOT AND or applying a NOT with other operators, looking at the bigger circuits or even the multiplexer. So you can think of like if you're building a house with bricks, right? The transistor is one brick. And you can have a group of bricks and you would lay the cement or whatever that you would need to lay the bricks on top of each other. And eventually you'll have a wall and then many walls. So these are the smallest components in the processor, and you can eventually build the larger circuits, which eventually give you computer hardware and components or computer hardware combined to give you your system. Okay. So as we look at this, and in some of the later upper classes, you're going to spend a little bit more time looking at digitals. Okay. So you have two sources of input. It would apply the logic that you would see with our operators to be able to give you some kind of output after as it comes. And this is the part of the simplest process in computing. Okay. Okay, so it shows you with NAND, NOT, and OR. Sorry, my computer is gonna need electrical source here. So take a look at this, okay? Now, the basic functionality, as we looked at the OR earlier, okay, so you need to know how to read these gates. So you have two input X and Y, and you have an output SE, whether it's 0 and 0, 0, 1, right? The OR, the way I use this, the gate structure, it looks like an arrow. So that's how we would draw it, okay? And then the AND, the shape of that looks like a D, but it also requires two input, and then it's gonna have one output. The NOT gate, the way that we would draw this is gonna be, usually you would see a small bubble, and it will be a triangle attached to a round circle, a small round circle, or just a circle. Okay. So when we do a NOT AND, we simply attach the NOT gate to the AND. Okay. So it's gonna AND it, and then it's gonna NOT here before it gives out the output. Okay. So here, what you would see is that we would have two input for the OR, right? And then it's gonna take the output for that OR, and it's gonna use another input, and it's gonna OR it again to give you the final result. So when you read this, you should be able to say, oh, that's an OR, that's an OR. So OR result from that, apply another input OR, and then have the output. So at the binary level, you would take 2 input in binary, get the result for the OR, take the result, apply it with another input, OR it, and then get the final result. In this one, it has 2 AND, so you would have 2 input for one, have the result, 2 input for another, AND it, have a result, and then AND those again to get the output. So we AND, and then AND at the end. Okay. And then similar to that, but in this case, we have output for one, combine it with another input externally, and so on. And then this one is a not and not and. And then the result for those are going to be OR. So NAND, NAND, and then OR. Okay. So that's how you would visualize the construction of the gate. Now you will find a lot of simulator online that you can play with this. You can apply the 0 and 1s for the input, and then it's going to give you the output as a result. So you can test it. If you search for like gate simulator, right? People created the software or online application for it. So you can just use the website, or you can download the app to do that. And then we also see where it becomes, right, constructed as a larger circuits, where you would see it as a multiplexer. And we'll touch on that next week. Any question? Okay. So I'll come back to this and then we'll review some of it, but I believe, let me see if I put that on here for you. I had put it on the Unit 1 notes. Otherwise, we would include it in the Unit 2. Yeah, gates and operator document, that's there. So similar to what you have seen on the website, right? You would see some diagram. And for the NAND gate, it is the opposite of the AND, right? We talked about how it ANDs it and then apply the NOT. So it's constructed from the AND attached to the NOT gate. So for final, you will likely see some of the gates. Okay, no problem. And you have to determine what that gates represent. Okay, so this one, it's a NAND because it's AND, like a D, right? I always think about the D in the word and then the bubble indicates that it's not. Okay. And then the OR looks more of like a curved arrow, and this is a NOR, so OR not. And sometimes it's drawn like this. Okay. And then lastly, before we go, this is an exclusive OR, or sometimes you would see it's written as XOR. So it tells you here that it is 1 if only one input is 1 or both. So the truth table for this is whenever, like very much like the OR, but in the case where if you have the 1 input or both of the input, you would have a 1. It is helpful in implementing binary arithmetic. When do you see that? When you do an adder. So earlier this week, I showed you how you would do the carry from to the left column, right? This is when we would implement exclusive OR to do an adder or a half adder to carry that bit to the left. Okay. And it tells you here that it gives the proper output, at least for the least significant bit, by adding 2 bits. And the AND gives you the output for the least significant bit by carrying 2 bits. So for the exclusive OR, right, The way it's drawn is it's an OR with a strike. Okay. So in this, in the adder, that what I was indicating earlier, when you do the half adder circuit, when you carry that bit to the next column and you operate it from the top, this is what would be for the circuit. You would have, right, an exclusive OR with an AND. This is how it is. So that way it will do the carry. Okay. So now we see it from a binary perspective, and when we do the arithmetic, now we can visualize it from with the gates and the operators. Okay. So there we go. This is a full adder. So when you add, right, to do a full adder to carry the ones, you would have the exclusive OR. This is the circuit. Any questions? We'll come back to this again next week. So take a look at it. I encourage you to read the chapters and then looking at the things that we covered today, review, and then also pre-read for the next chapter. I put the notes in the note pages to help you kind of just summarize, but the chapter also contained a lot of good content. So, okay. All right, that concludes my session for today. Make sure that you put your name into the chat for attendance. Please let me know if you have questions. I'll stick around for a few minutes. Let me stop recording. And then if you need to see me during office hours, please do. So have a good weekend. Don't forget Monday, no class, Friday, no class, holiday, but we have class on Tuesday.